Welcome to The Explainer. Today, we're going to totally demystify the immense geological forces constantly churning right beneath our feet. You know, we walk around every day assuming the ground is completely permanent and unshakable. But the reality? Our planet is incredibly dynamic. We're going to look at these massive forces not just as random acts of nature, but as a fascinating, terrifying, and totally logical chain reaction of energy. By the end of this, you'll see exactly how a completely silent shift deep underground can unleash a cascade of destruction across entire oceans.
So, here's our game plan for today. We'll be walking through four main areas: the anatomy of an earthquake, how we measure the shake, pinpointing global and local danger zones, and finally, looking at the massive tsunami ripple effect. Let's get right into it.
All right, part one, the anatomy of an earthquake. This is the initial spark of the chain reaction.
To really wrap our heads around the sheer scale of these events, we have to start incredibly small. We need to zoom all the way down to the microscopic breaking point of solid rock. Fundamentally, an earthquake is just a sudden release of pent-up energy. But the absolutely crucial phrase here is that the waves travel in all directions. It's exactly like dropping a heavy pebble into a perfectly still pond. The energy doesn't just sit there, it rapidly expands outward. Beneath the Earth, this energy generates seismic waves, radiating globally in a 3D sphere, and that expanding ripple is the driving force behind the whole shebang.
Now, this actually clears up a huge misconception. You hear the word epicenter on the news all the time, right? But that's really just a surface marker. The real action happens deep below, at what we call the focus, or hypocenter. That's the exact invisible point underground where the rock finally snaps. The epicenter is just the spot on the surface directly above it, and since it's closest to the blast, it's typically the very first place to get hit by the destructive waves. And honestly, how deep that focus is makes a massive difference to us up top. Deep focus earthquakes, we're talking 300 to 700 kilometers down, are rarely destructive. The seismic wave naturally weakens or attenuates over that immense distance. But shallow earthquakes, the ones originating less than 60 kilometers down, those are the ones that absolutely devastate our cities. There's just literally no room and no time for that violent energy to fade before hitting our infrastructure. So what actually pulls the trigger on that initial snap? Well, the vast majority are triggered by tectonic activity, colossal rock plates just grinding relentlessly against each other. Volcanoes do it too, but incredibly, human actions can be the spark as well. The immense weight of water from a large artificial reservoir, intense underground mining, or massive shock waves from chemical or nuclear explosions can absolutely unleash this pent-up Earth energy. Okay, moving on to part two, measuring the shake. How do we quantify these unseen forces?
We know where the energy comes from, but think about it for a second. How do we actually measure the invisible? When the ground is violently shaking and everything is falling apart, how on earth do scientists step back and turn that absolute chaos into neat, objective data?
It turns out we use two totally different scales for this. The Richter scale is all about measuring the raw energy or magnitude of that initial spark. It's recorded by a seismograph on a base 10 logarithmic scale, which means a 3.0 is 10 times stronger than a 2.0. That gives us one constant value for the whole quake. The Mercalli scale, on the other hand, measures the tragic human reality of the ripple. It's based entirely on observed destruction, rating from Roman numeral 1 to 12. So the Mercalli number varies wildly. It could be an 8 right near the epicenter, but only a 2 in a town 100 miles away.
Let's jump into part three. Global and local danger zones. We're mapping out the Earth's powder kegs. Zooming out for a second, it's really important to realize that earthquakes definitely don't just happen at random. They follow extremely distinct patterns known as seismic belts. A staggering 65% of all global earthquakes happen in just one zone, the Circum-Pacific Belt. The mid-continental belt comes in a distant second, at 21%, with the Mid-Atlantic Ridge and a few other areas making up the last 14%. Now, you probably know this massive Circum-Pacific Belt by its much more famous name, the Ring of Fire. It is basically a continuous engine of global friction. It traces the coastal margins of the Americas and East Asia, capturing massive features like the Rockies, the Andes, Japan, and the Philippines. This belt represents convergent plate boundaries. That means the Earth's plates are aggressively colliding, forcing one underneath the other and constantly resetting the timer for the next major seismic event.
Let's bring this down to a local level and look at India as a prime example of living with this reality. The country is split into distinct risk zones based on historical data.
These range from the relatively quiet Zone 2 in places like Karnataka, all the way to the extremely volatile Zone 5. Zone 5 carries a very high damage risk, encompassing the entire Northeast, Kutch, and the Andaman and Nicobar Islands. And honestly, even massive population centers like Delhi sit in a high-risk Zone 4.
When you actually add all those risk zones up, you arrive at this pretty wild statistic. 59%. Nearly 60% of India's total landmass is liable to seismic hazard damage. We're not just talking about abstract geology here. More than half of the country physically sits right in the direct path of potential seismic ripples. It makes infrastructure planning literally a matter of life and death. Which brings us to our final section. Part 4, the tsunami ripple effect, the final, devastating wave.
So what happens when this violent energy doesn't just shake the dirt, but displaces billions of gallons of ocean water? You get a tsunami. It's a Japanese word meaning harbor wave, and it describes a series of extremely long-traveling ocean waves. But keep in mind, not every earthquake generates one. For this specific nightmare scenario, 3 things have to perfectly align. The quake must be located under or very near the ocean. It has to be massive in magnitude, and crucially, it must create a vertical movement in the seafloor. Let's walk through exactly how this terrifying physics plays out. Step 1. Tectonic plates snap, vertically shifting the seabed. It acts like a giant paddle, instantly displacing an unimaginably massive column of water. Step 2. That energy transfers directly into the water and large waves ripple outward. Step 3 is crazy. In the deep ocean, this wave is barely noticeable on the surface, but the energy underneath is silently racing across the globe at up to 800 kilometers per hour. That is literally the speed of a commercial jet. Finally, step 4. As it reaches shallower coastal waters, friction slows the wave down, which forces all that incredibly compressed energy upwards, drastically multiplying the wave's height. It's essentially a shallow water trap. The local geography completely dictates the level of destruction. Reefs, bays, and the slope of the beach take that fast-moving deep water energy and squeeze it into a much shorter distance. The water simply has nowhere else to go but up and then fiercely forward onto the land, transforming what was an invisible ocean pulse into a towering wall of destruction. So bringing it all together, we're looking at a massive interconnected chain reaction. That initial invisible spark underground cascades into a total nightmare of effects. It starts with deformed ground and shattered structures, but it quickly triggers secondary horrors. Severed gas lines cause massive fires. Loosened earth creates devastating landslides, and displaced waters unleash flash floods and tsunamis. Ultimately, it all culminates in the tragic loss of human and animal life. It perfectly illustrates how deep Earth geology connects directly to our own vulnerability.
Look, we simply cannot stop the Earth from moving. The plates are going to keep colliding, pressure will continue to build, and that energy will inevitably be released again. Understanding this unstoppable chain reaction isn't just a geography lesson, it's about survival. The science is clear, the danger zones are mapped, and we know exactly how this energy travels. So the real question we're left with is this: knowing what we know about the awesome, unstoppable power of our shifting planet, how will we engineer our world to withstand the rippling energy next time?